Hello students, welcome back. We completed section 1. Now let's go to section 2, Logic and Foundation. Before starting, there is a debate or controversy, whatever you may want to call, that whether we should do set and relation first and then logic and foundation, or vice versa. As a matter of fact, the answer is kind of like chicken and egg. Set and relations brings about logic and foundation, and also vice versa. Logic and foundation is necessary to build set and relations, and also vice versa. And I did whatever I wanted. I decided to go with set and relation first, and then doing logic and foundation. If I remember correctly, you did it the other way around in Introduction to Proof class. At least there are many textbook authors do it the other way around. Logic first and sets later. I just did one way. It's not always right or wrong. It's just kind of like chicken and egg. Okay, alright. Let's begin section 2, Logic and Foundation. First, propositional logic. What do you mean by proposition? What do you mean by compound propositions, logical operators, things like those? You should remember all those. A proposition or a statement is a mathematical sentence that is either true or false. Not both, not neither. Kind of like set an element. A should be an element of a certain set or not. Not both, not neither. And then if you have multiple propositions, you can compound those together using logical operators such as these. Standard 3, negation, conjunction, and disjunction. Negation, not P, goes like this. True becomes false, false becomes true. By the way, if you use digital logic, 0 is false and 1 is true. And then here's the Venn diagram associated to that. Conjunction, A and B. P and Q. In terms of set theory, A and B is usual, but for propositional logic, P and Q is usual. Truth table is like this. In order to have a truth, both must be true. And also look at the Venn diagram. Should be inside of both, only here. Otherwise, false, false, false. False, false, false. That's conjunction, P and Q. Finally, disjunction, P or Q. It's a union. We have true all the way except the last one, or false. That corresponds to the outside here, the white region. Otherwise, T, 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 T. These are standard 3. There are 2 more. Conditional and biconditional, or implication and equivalence. And we call these logical operators fundamental 5. 5 fundamental logical operations. First, negation. Second, conjunction. Third, disjunction. Fourth, implication. And fifth, equivalence. What is implication? It works like this. If P then Q, if both are true then true, that's easy to understand. True then false, that's false. If false, then whatever what you do in the conclusion parts, always true. Some people get a little bit confused here, but one way to understand it is this. If I give you a wrong problem, the problem that is false to begin with in an exam, then no matter what you attempt, you should get full credit. Somehow you get it right, or somehow, well, usually you will get it wrong, but either way, it must be full credit because I'm the one who screwed it up, all right? If my problem is correct, legitimate, and you got the truth, then of course you get credit. You failed it, and you're not going to get credit. That's a good analogy. Here's Venn diagram associated to that. That's implication. By the way, I use the term condition and conclusion. The P part is called the condition, and Q part is called the conclusion. The condition and conclusion. You can read through this notebook. That's implication. Now finally, equivalence. Equivalence is, as a matter of fact, a compounded statement of this implication. If P then Q, and also the other way around, if Q then P join together with conjunction. So this equivalence is actually not a standalone logical operator. This one and that one put together, like this. If P then Q, and if Q then P put together. Here is the truth table. And if they are both true, then true. Both false, then true. If they're different, then false. That's why this thing is called equivalent. Whatever P is, whatever Q is, they must be the same, then true. Different, then false. By the way, did I say this equivalence is not really a standalone logical operator? It actually comes from a compounding of implication, one direction and the other direction, with conjunction. Not only equivalence, implication is also a compound statement too, as a matter of fact. It is not a standalone operator. Here's an example. Not P or Q, truth table is like this, or not P and not Q. Truth table is like that. They are the same, TFTT, TFTT. And let's go back to this implication, TFTT. Remember, they're all the same. So if P then Q, or not P or Q, or not P and not Q, they're all the same. This operation, by the way, P and not Q, this is called NAND operation. P NAND Q. And it turns out that's the most fundamental. As a matter of fact, I said it wrong. It's not really the most fundamental, but you can restructure everything so that you can make that NAND operation the most fundamental. So what I told you earlier is equivalence is not really a standalone operation. Implication, that's not really standalone either. So everything can be written in terms of these standard three, not fundamental 5, but it turns out we don't need all three. You need only NAND operation, this one here. It turns out this one is sufficient for everything. Turns out everything can be written in terms of repeated application of NAND operation, negation, conjunction, disjunction, everything. And that kind of thing is important for computer scientists, especially for data compression and things like that. But let's not go too deeply into that. Basically, analogies like this, if you have some compounded logical statement or long program or whatever computer scientist people call, if you re-express everything in terms of NAND operation only, then basically you're looking at a long sentence or paragraph with only one type of verb. So you don't really have to specify all the verbs. Just take the spaces and then list only consonants. That way you can compress your data a lot. And that's only one example of many for this NAND operation. And that kind of thing is actually being used in NAND flash memory and things like those. Anyway, let's not go too deeply into this computer science business. This is a math course, so let's not get too carried away. Where was I? Yeah. We talked about fundamental 5, negation, conjunction, disjunction, not, and, or, and then conditional, biconditional, or implication, equivalence, if then, if and only if. Okay. Final topic. If you have an implication, if then statement, or conditional statement, then The other way around is called the converse, if Q then P. And same direction but negated, not P then not Q, is called the inverse. And opposite direction and also negated, not Q then not P, is called contrapositive. And then here is the combined truth table. And what do you observe? The original conditional statement, if P then Q, and its contrapositive are identical, TFTT. So they are the same. So if contrapositive is easier to handle, then you can prove some conditional statement using its contrapositive. And if you compare the original conditional statement with its converse, they're not the same. So if you have to prove the converse, here's a new problem. You have to go through that separately. And of course, if you take the contrapositive of the converse, you end up with the inverse. These two are the same. Okay, that was a subsection 1, propositional logic, and we have enough time for maybe a little bit more. Let's talk about some propositional equivalences, tautology and contradiction. A compound proposition that is always true is called a tautology, and always false and is called contradiction. Looks like those are trivial, but it turns out the tautology is very, very useful for us, especially when we combine that with a conditional statement. Let P and B be compound propositions. We say P implies Q if the conditional statement P then Q is a tautology. So if P then Q is always right, then we use not just this arrow notation, but we use double arrow notation. And then instead of calling P and Q as condition and conclusion, we call them sufficient condition and necessary condition. Sorry about those terminologies. Previously condition and conclusion, but now both are conditions and one is sufficient, one is necessary. Oh, what is this? I'm sorry, I did not invent any of those terms. You just have to get used to those. And the reason that we do not have conclusion is because in practice, you have many of these. One step and the next step and third step and the fourth step, and then it may go for 25 steps or something like that. Very last one is the conclusion. Everything else before that is just the next step. We don't want to use conclusion in step 7 of total 25 or step 17 of total 25. Or the last one is the conclusion. So they're all conditions. Before, sufficient, after, necessary, and then we go to the next step and the next step. That's a justification. Otherwise, you just have to get used to these. By the way, in this course and actually all other math courses, 90% of what we do is going to be proving this conditional statement being tautology or not. That's 90% of the proof we do. What is the other 10%? It's going to be this. If and only if is a tautology. We say logically equivalent, but this is actually the same as if P then Q is a tautology, and also vice versa, if Q then P is tautology. So, this is actually these put together twice, so you can say 100% of what we do is this, with some exaggeration. So is that important? We're going to come back and talk about the importance of the tautology putting into this a little bit later in subsection 2.3. But for now, let's take a break.